Good morning. Our topic is about causation of epidemiology, and the presenters are me, Harinashri Ravi, Bukke Bharat Nayak, Akshita Chilwal, Om Dukesh Soratia, Alekia Duduka, Jahnavi Singh. And now let's discuss what are the topics included in our presentation. They are introduction, concept of causes, single and multiple causes, and factors of causation, interaction, guidelines for causation, and the conclusion. Now let's go into the topic, that is introduction. A major goal of epidemiology is to assist in the prevention and the control of disease and in the promotion of health by discovering the causes of disease and the way in which they can be modified. And when it comes to the genetics, it is physically, biologically, and socially affected.
My name is Akshita and my subtopic is concept of cause. An understanding of the causes of disease is important in the health field, not only for prevention but also in diagnosis and the application of treatment. And the study of causes of disease and their origin is called as etiology. So how would we define the concept of cause or cause? A cause of disease is an event, condition, or characteristic or combination of all these factors that plays an important role in producing in production or producing the diseases. And a cause can be of two types, sufficient or necessary. रुक जा भाई. So now moving on to the two causes. The first one is sufficient cause. It is a cause is said to be a sufficient cause when it is certain that it will produce disease. So it is a minimum set of conditions, factors, events that are needed to produce a given outcome. It is not a single factor, but it is composed of several components. For example, cigarette smoking is one of the sufficient cause in lung cancer. Generally, it is not necessary to identify all the components of the sufficient cause before before the prevention can take place. It is because since the removal of one component can interfere with the action of the others and thus can prevent the disease. Uh, that can prevent the disease. And the second one is necessary cause. A cause is necessary if a disease cannot be initiated or developed in its absence. We can say that the necessary cause is a causal factor whose presence is required so that the disease can occur or come into full effect, or effect. So if a disease does not develop without the factor being present, then we can term that factor as necessary cause. So now coming to the conclusion of both kind of causes, sufficient cause is a cause that is certain that it will produce a disease, and necessary cause is a disease without which is a cause without which disease cannot be developed.
Hello everyone, myself Jahanvi Singh, and I'm going to continue with our next topic, that is single and multiple causes. So according to Pasteur's work on microorganisms led to the formulation, first by Hanley and then by Koch, of the following rules for determining whether a specific living organism causes a particular disease. So the rules are as follow. Firstly, it must be present in every disease case. Second, it must be able to be isolated and grown in pure culture. Next, it should cause specific disease when inoculated in susceptible animal. And lastly, it must be recovered from the animal and identified. So now next, as a given disease, it can be caused by more than one causal mechanisms, and every causal mechanism involves the joint action of a multitude of component causes. As for example, in single or multiple causes, a single cause involves one-to-one association, that is specificity, and in multiple it includes epidemiology trade, sufficient and necessary cause, multifactorial causation, web of causation, and interaction. So in single causation theory, it does not explain the causation of non-communicable diseases, whereas multiple factors are involved in causation of disease. And on the other hand, multifactorial causation, it includes multiple factors lead to the disease, common in non-communicable diseases. For example, smoking, air pollution, and exposure to asbestos leads to reaction at cellular level, which leads to the lung cancer. So now coming on the limitation part, anthrax was the first disease demonstrated to meet these rules, which have proved useful with other infectious diseases. But for most diseases, both infectious and non-infectious, Koch rules for determining causation are inadequate. So this limitation includes: firstly, the causative organism may disappear when the disease develops. Secondly, the certain microorganism cannot at the present time be grown in pure culture. And lastly, not all organisms exposed to an infectious agent will acquire the infection. So that's all from my part. Thank you.
Good morning. My name is Dialekya. I'm from Group 3. Our topic is about the causation of the epidemiology, and my subtopic is factors in causation of the epidemiology. There are four types of the factors which play important role in the causation of this disease. All are maybe necessary, but they are rarely sufficient to cause a disease. So first one is the predisposing factors, second one is the enabling factors, third one is the precipitating factors, and fourth one is the reinforcing factors. Let's get in detail about each factor. Here comes the first factor, that is the predisposing factor, in which it creates a susceptibility for a disease agent, like the example age, sex, previous illness. So these may not have the direct bearing on the cause of the disease, but they may cause the other risk factors like the salivary gland disease for carriers development. Let's go to the another factor. So here comes the second factor, that's the enabling factors. In enabling factors, environmental conditions which favor the development of the disease, like they favor the environmental conditions. Enabling factors means, so like example, low income, poor housing, poor nutrition, inadequate medical facility. So, so many number of models for this disease causation has been proposed, and among these models, one of the simplest one is the epidemiologic triad or the triangle, the traditional model for infectious disease. These two are the simplest one among the number of the models in the disease causation. And the triad for this consists of the external agent, which is a susceptible host, and also the environment that brings the host and agent together. This environment brings the host and the agent together. Let's go to the other factor. Here comes the third factor, that's the precipitating factor. It is a specific one or the noxious agent in which it can be exposure and also associated with the onset of a disease, like example, pollens in asthmatic attack. So here you can also see in this picture what are the side effects of the asthma triggers, like stress, anger, pollution, dust, cholera, toxin frame, uh, pollen, etc. etc. Let's go to the other factor, the last factor. So here is the last factor, which is the reinforcing factor, in which these factors get aggravates already established disease or the state, like the example repeated exposure and unduly hard work. You can also see in this picture, you can replace this text, you can, yeah, text, you can replace it. It's a repeated process. Reinforcing factors means it's a repeated exposure, repeated disease. So the term risk factors are those factors that have a direct link to the cause of the disease but are not sufficient to cause of the disease. So The term risk factors means these are the factors which have direct link to the cause of the disease, but they may be not sufficient for this cause of the disease. They heighten the chance of the contacting a disease condition, but not themselves. Like example, refined sugar, time, bacteria for caries, etc. So that's all for my presentation. Thank you.
Topic is interaction. The necessity of a causal partner for disease occurrence is what we mean by biologic interaction. Thus, the very definition of a cause in risk factor epidemiology places the issue of interaction front and center. It is assumed that virtually all disease arise from the interaction of two or more causes. Despite the centrality of interaction to this causal framework, methodologic advances have focused mainly on the isolation of single causes and the identification of individual risk factors that contribute to disease occurrence in a population. New designs were developed to allow us to see the relationship between exposures and disease in our data that would provide clues to identification of these causes. Statistical methods were developed to aid in causal inference. What follows is a discussion of this newer way of thinking about how to identify biologic interaction. I prefer the use of the term synergy in this discussion because it is more neutral to level of organization at which interaction is being described. Although these methods have developed separately from those in the field of genetics, they are fully applicable to the field. Thus, epidemiologic approaches to interaction provide an exciting perspective on genetic concepts that may shed new light on genetic issues. Likewise, the integration of genetic thinking into epidemiology can advance methodology.
Good morning, I'm Harinashri and I'm going to continue with the guidelines for the causation. Bradford Hill in 1965 suggested that the following aspects of an association be considered in attempting to distinguish causal from non causal association. Those are temporal relation, plausibility, consistency, strength, dose response relationship, reversibility, and judging the evidence. Let's see these all by one. The first one is the temporal relationship. It refers to the necessity for a cause to precede an effect in time. This is usually self evident, although difficulties may arise in case control and cross sectional studies when measurements of the possible cause and effect are made at the same time. And the effect may, in fact, alter the exposure. For example, a use of seat belt, and the next one is a plausibility. An association is plausible and more likely casual if consistent with other knowledge. Problem with plausibility is it is too often not based on logic or data but only on prior beliefs, a lack of which may be a simple reflection of medical knowledge. And the next one is consistency, refers to the repeated observation of an association in different populations under different circumstance obtained from different studies. And this is also the lack of consistency, however, does not rule out casual association, because different exposure levels and the other conditions may reduce the impact of the casual factors in the other causes. And the next one is the strength. Hill's argument is that a strong association between possible cause and the effect are more likely to be casual than the weak association. The fact that an association is a weak does not rule out a casual connection. For example, would be a passive smoking and lung cancer. And the next one is a dose response relationship. Dose response relationship occurs when changes in the level of a possible cause are associated with changes in the prevalence or incident of the effect. And the next one is reversibility. When the removal of a possible cause results in reduced disease risk, the likelihood of the association being casual is strengthened, and cessation of smoking reduces the risk of developing lung cancer. And the next one is the judging the evidence. There is no completely reliable means of establishing a casual relationship, and sometimes evidence can be conflicting. To make a causal inference, all available evidence must be considered, and the correct temporal relationship is very essential before other criteria are considered. For example, plausibility, consistency, and due response relationship. And the likelihood of a causal association is heightened when many different types of evidence lead to the same conclusion.
Examples of causation relations. Thus, the philosopher seeks definition while epidemiologists construct the causal models. However, we have argued that epidemiologists believe an assumption about the case cause carry particular consequence, but the causal models are constructed within the limits set by the definition of the epidemiologist has in mind, whether it is explained or implied. Thus, if the deterministic definition of the caution is assumed, only the deterministic model will be recognized as causal. Because the caution is so central to what the epidemiologists do, we argue that it is crucial that epidemiologists understand the implications of the application particular definition and causes. We argue for using the probabilistic definition of caution because it is more inclusive than the necessary and the sufficient component cause the definition. Deterministic model can treated as extreme cases of the probabilistic definition. Thus, the probabilistic definition incorporates the concept of the necessary and sufficient cases. In addition, there are some concepts, while insufficient for defining the caution themselves, that cannot be dispensed with in an causal definition counterfacts production and temporality. Additionally, the probabilistic definition does not require assumption about the hidden biological mechanism that observed probabilistic phenomena waves reduced to some underlying deterministic mechanism. Nevertheless, a definition is not itself a theory caution. There is more conceptual work to be done towards further specifying the nature of the caution. Unfortunately, physiological thinking about the caution has been largely driven by the physical science, focusing on simple chain of event rather than the complex multi-level relations that make up biology. This is an area that need further research. How are the explanation at divergent levels, from the molecular to the social, are related, and further inquiry is needed into the relation between the concept of caution and the causal inference. Guidelines for drawing causal inference may differ according to how caution is defined. Because causal inference is at the heart of what epidemiologists do, the theoretic study of caution has important consequences for the everyday practice of epidemiology.